Antenna polarization refers to the physical orientation of the radio wave's electric field as it travels through space. When an alternating current flows through an antenna's elements, it creates an electromagnetic wave consisting of two fields, an electric field, E field, and a magnetic field, H field. These fields always travel at right angles to each other. By definition, the polarization of an antenna is determined solely by the orientation of the E field relative to the Earth's surface. The magnetic field is always perfectly perpendicular to the electric field. If your antenna is horizontally polarized, its magnetic field is vertical. Most common terrestrial antennas use linear polarization, meaning the electric field oscillates in a single straight plane. Horizontal polarization. The electric field is parallel to the ground, red color in the visualization. If you string up a wire dipole for 80 meter or 160 meter parallel to the earth, the wave it radiates is horizontally polarized. Vertical polarization. The electric field is perpendicular to the ground, red color in the visualization. A vertical whip antenna mounted straight up produces vertically polarized waves. The mismatch penalty, that is cross polarization loss. For direct line of sight communications like ground wave or VHF or UHF simplex, the transmitting and receiving antennas must have matching polarization. Trying to receive a horizontally polarized signal with a vertical antenna results in severe signal attenuation, often a drop of 20 decibels or more, which is enough to wipe out a weak signal entirely. For HF skywave propagation, the ionosphere completely scrambles the wave's polarization as it refracts back to Earth. So matching polarization on the receiving end is far less critical. Circular polarization. Instead of staying in one fixed plane, the electric field can rotate in a corkscrew pattern as it travels forward. Depending on the direction of rotation, this creates either right-hand circular polarization or left-hand circular polarization. Circular polarization is incredibly important for specific applications like satellite communications. When working LEO or low Earth orbit satellites, the spacecraft is often tumbling in orbit and the signal passes through the ionosphere, causing the polarization to constantly twist, a phenomenon called Faraday rotation. If you attempt to receive that signal with a standard linear antenna, the audio will constantly fade in and out as the satellite's orientation shifts relative to yours. To combat this spin fade, ground stations use circularly polarized antennas. Alternatively, operators using directional linear arrays like a handheld Moxon-Yagi hybrid must physically twist their wrists, rotating the antenna in real time to match the satellite's shifting polarization and maintain the link.